Welcome to this webinar where we'll focus on Grundfos e-solutions in daily terms, called e-solutions. What we mean by that is that we have a number of pumps which is equipped with motors where we can run the motors with variable speed. But why do we actually do that? Well, before we answer that question, we need to take a close look on what is determining the flow in a hydronic system. We'll just make a short sketch here. If, for instance, we have a chiller, a boiler, whatever, something where we need to distribute the energy to a system, we equip the system with a pump, and then we circulate the pump out to the system and back to the chiller or boiler again. But actually, typically people tell us that, okay, the pump is the only piece of equipment which is determining the flow in the system. But that's not the case, because when we have a radiator or air handling unit or whatever we have in the system, we always have some kind of dynamic valves. And these valves are opening and closing depending on the actual load in the room. How many people is occupying the room, how many computers is engaged, the amount of sun radiation from windows, etc. is determining what is the actual need out here. And if the need is going down, the valve is closing. Okay, how does that cooperate with a traditionally fixed speed pump? First, we draw a pump curve which is looking something like this. We circulate some flow. We have our pump curve as we know it, and the calculation about on how much water we need to circulate is done very traditionally. We calculate the maximum cubic meter per hour or gallons per minute or liters per second, whatever we prefer. But it could at least be something like this. And then we calculate what is the pressure loss in our system here. The pressure loss will then tell us how much pressure does this pump actually need to be able to deliver to the system in order to make it flow in the right way as we want it to be. So when we have this point out here, we could draw what we call a system characteristic. But as we just explained, the circulating flow is not a fixed value. The flow can go up and down depending on the need in the system or in the rooms, etc. So if this is at our maximum situation here, we know that the flow can only go one way, and that is towards zero flow. And that's something the pump is perfectly capable of handling. But what is happening is that when the valves is closing and we have a pump which is operating at the same rounds per minute, the fixed speed all the time, the only thing the pump can do is to start to increase the pressure as the flow goes down. So this was what we needed in terms of pressure at maximum load. But when the flow need is at minimum, actually a normal pump, a fixed speed pump, will deliver this much differential head. So what we can see is that a fixed speed pump does the exact opposite thing of what it should do, as it would be more optimum to follow this line, but instead it increases the pressure. So as we go along to zero flow, we simply just increase the problem and deliver more and more differential head. So all of this here, you could say, this is actually equivalent to wasted energy. So what can we do about that problem? Well, I think we need to erase this and draw a new pump curve. So we'll try to draw a new pump curve, which actually looks quite a lot as the same as we just saw. We have the same maximum curve here. So this is our starting point, so to speak. But what we now have is that we have a pump with a built-in frequency drive. And what that does is that it allows us to adjust the maximum curve here actually downwards to 0. But that's not something we typically see. But what we do is that when we have like a maximum situation where we need this amount of flow and this amount of differential pressure or head in daily terms, then what we can do is that we can tell the pump to operate based on what we call constant pressure. And what that means is that as the load is going down, the need for flow is going down because these already mentioned valves are closing. Then instead of starting to increase the pressure, the pump will adjust its maximum curve according to this, and all times securing that the duty point will be on this line here. And the duty point, remember, is the cooperation or the cross point between pump curve and control curve here. So in this case we have saved all the energy which is related to this area up here. But we don't only have constant pressure curve, control curve. We also have something which we call proportional pressure. And what that means is that it's a basic, just the next generation of constant speed or constant pressure, so to speak, sorry. And what it does is that when the same valves again are closing, instead of providing the system with constant differential head here, it reduces the head according to the set point, which is out here. And maybe this could be a good opportunity to mention that the set point for a pump is always related to what it is here at the maximum curve, at least while we are talking about magnet pumps. So if, for instance, we are delivering 6 meters of water column out here, 60 kilopascal, then we will deliver 3 meters water column at 0 flow here. And you might answer or ask, where should we use which control function here? I would say that one idea is that if we have like a floor heating system where we have multiple rooms, each served by each floor string, and we have pipes on the return. So in order to illustrate, we could have like this. So this could be represented by one room, right? And that's the same for all of these strings here. Then the way it works is that we have a control valve here, which is always monitoring what is the flow temperature. But that's not so important right now. But what is the case is that this piece of equipment here is very close. So the pressure loss in this small circuit here will be the same, even though that the flow can vary. The flow can go up and down according to these valves here, which are opening and closing. But the pressure loss will always be the same, at least if it's commissioning correct. So in a case like this, we operate the system with constant pressure. So proportional pressure, where should we use that? That's more like if we have a very widespread system where there's a long distance from the heat source or cooling source and out to the final consumer, where you have different consumers on the way out here. There might be several meters out to the last consumer here. So that means that depending on how all of these different consumers here are consuming more or less water, the pressure loss in the main pipe here can be high or low. So in a case like this, we need to adjust the control curve so that at maximum flow we deliver exactly the pressure loss which is calculated to be to the furthest point in the system, but also so that when the pressure loss is very low, then we adjust the pressure delivered by the pump to the minimum. And that's where we use this proportional pressure. And a way to show that is that, okay, when we operate the pump on proportional pressure, then we have an additionally saving. So what you can see here is that when we have the system characteristic, is that when we have a speed control pump, we are much closer to operate the pump according to the system characteristic compared to what we did while we had the fixed speed pump. So that's a huge benefit to the use of energy for the pump. But also one other very important element is that the stress on the dynamic valves and other vital equipment is going down while we are operating the system with a speed control pump. So what other possibilities do we have? Well, there's one more control function which I would like to mention, and I think we have to start all over again a little bit, and that is that in some cases we have what we could call a fixed need for flow. And if we have a fixed need for flow and the flow is not variable, then you might say, okay, why don't we just choose a fixed speed pump then, because that's the most optimum case. And sometimes it can be a good idea, but in others it's actually not so clever, because if, for instance, we have a need which is right here, then if we do nothing, then what will happen is that the system characteristic will most likely look something like this, which means that instead of having the pump to deliver exactly the flow we need, it will deliver slightly more, meaning that the conditions for our cooling coil, our heat coil or whatever will not be as intended. So in order to avoid that, what has been a practice in the industry for years is to, instead of having this situation, we kind of secure that we are not delivering more flow than what is intended here. So that means that we are increasing the pressure loss in the system by throttling a valve, so we meet exactly this duty point here. So here we increase the system characteristic and secure that we have the same amount of flow. It's doable, but we have a third option, which I think is better. And that is also due to the fact that we now have our Magna pumps with speed control and with a permanent magnet motor with very low energy consumption in general. So what we do is that if we have this need here and we know that we have a system characteristic which is determining that we need this this pressure according to this flow here. So what we actually do is that we are still telling the pump to operate with a constant curve, but then we are just adjusting the curve downwards until we reach this duty point here. And then the pump is still operating with fixed speed. So if this is 100% rounds per minute, this one could just as well be maybe 70%, and that's equal to saved cost of pump operation. And also the fact that we in the other situation needed to equip the system with a balancing valve or throttling valve, this valve can now be eliminated from the system. So we're saving initial cost here. Small break before we take the last part of the session here. So what we have seen until now with our speed control pumps is that I have shown you the functionality in our magnet pumps, or at least what we call Series 2000 pumps. But I would like to draw the attention to one other possibility which we have, and sometimes I feel it's slightly overlooked. But if we have like a pump operating in a system, we need to remember that what the pump is actually doing is that it is providing the system with a certain level of differential pressure, delta P. And as we go out in the system, this delta P is decreasing until we reach the final consumer, radiator, air handling unit, whatever in the system. So the pressure is decreasing. And this is about the level of how much differential pressure should we set the pump to operate by when we, for instance, have a magnet pump with proportional pressure, etc. It can be quite hard to determine how much pressure is the system actually needing. But what we could do, if we can persuade the consultant engineers or whoever is taking these kind of decisions, is that we ask the designer, where do we have our critical point in the system? And maybe he tells you that's 75 meters away from the pump, but we actually do have like a SCADA system looking over the whole system. So we could actually monitor the delta P on the critical spot out here. What we could do with this signal here is that we could transform this signal back to the pump, and that typically that's 4 to 20 milliamps, but that's really not what I'm focusing on here. But if we do this, monitoring the pressure, the differential pressure needed at the critical spot in the system, then what the pump will do is that it will not need this kind of control curve, but it will allow the pump to operate on the exact system characteristic. So that if we tell the pump you should at all time maintain like 2 meter water column or whatever out here, then these 2 meters will be what we call the foot point of our control curve, and everything else is then taken care of. So that is the bulletproof way to operate a pump, where you also at the same time know that the cost for operation is as low as possible for the pump. That's one thing. But then the last part, which I think we need to just touch a little bit, is that What about the pump operation and the efficiency on the pump, and what kind of implications in terms of energy used for the pump while it's speed control? We will end this session by focusing just a little bit on that, and I think that's where we nail why it's so important that we focus on this speed control of pumps. So when we speed control pumps, there are some way to explain what are we achieving or what is happening in terms of delta P and power consumption, etc., while we are speed controlling pumps. And this is quite interesting actually, and one of the main reasons why it's so obvious that we should do this. If, for instance, we lower the flow to 50% of the design situation by speed controlling the pump, then what we will get is that the head or the differential pressure delivered by the pump will then drop to 1/4. And that is actually exactly what the system characteristic will tell us that it should be. So we are not underperforming here at any point. But what is really important and interesting to know is that when it comes to power consumption for the pump, illustrated by this P here, it will drop to 1/8 of what it was initially. So here we can see that in terms of energy savings, there is a massive energy saving we can gain by utilizing these speed control pumps. We have speed control pumps with prefabricated variable speed motors from all the smallest ones and all the way up to 22 kilovolts. That means where it's all packed in one unit. When we go above 22 kilovolts, we need to have a wall-mounted variable speed drive on the wall. But the point here is that there is massive energy savings to gain if we utilize this fact that we save a lot of energy while we have speed control pumps. Thank you very much for watching today. I hope to see you soon in the next webinars, which soon will be published too. Thank you very much.